Greetings and welcome to this lecture. We are in module 8, lecture number 5, that is channel length modulation. In this lecture, we will see the basic phenomena of channel length modulation defined as CLM, and also how this channel length modulation affects the drain current model. These are the learning outcomes of this lecture, which helps you to understand what is the physical origin of CLM in short channel devices. This will also help you to distinguish this CLM phenomena as compared to other short channel effects such as velocity saturation and dibble based on their impact on IDVD characteristic. Let us do a quick recap. In previous lecture, we were discussing about velocity saturation. We said that when you reduce the channel length, then the electric field in the x direction, which is Ex, is very high, and hence the carrier velocity, the drift velocity, is no longer proportional to Ex. It means it will not linearly rises with Ex. After a certain Ex value, it gets saturated. We also defined a critical field Ec, above which my velocity is saturated to its maximum value. Then we said that we can incorporate this velocity saturation by considering a simple model of Vd, which is Vd max Ec divided by Ex divided by Ec divided by 1 plus Ex divided by Ec. Later we said that the better idea or better approach to incorporate this model with a fitting parameter n, where n is equals to 1 for holes and n is equals to 2 for electrons. So when you incorporate this model in your basic, then you will get the current equation with velocity saturation is equals to the current equation without velocity saturation divided by this factor. This model in two sense is good, as it will give you an accurate result compared to the model which we have derived as IDS without velocity saturation divided by 1 plus VDS divided by Ec into L, and it will also solve numerical issues or convergence issue, because in general we are also interested in the derivatives of dId by dVds or d square id divided by dVds when you incorporate these devices or models in the circuits. Later we said that the transition from non-saturation to saturation, when you incorporate the velocity saturation effect, is very smooth. It is gradual, because near the saturation region the product of Qi dash and Vd is gradually performed in such a way that Qi dash will go to its minimal value and Vd is going to its maximum value, attain its saturation value as Vd max. So this phenomena is gradual, and hence there is no need of calculating a sharp or abrupt value of Vds dash. The third thing we have calculated as the spacing between the current is no longer dependent on Vgs minus Vt whole square, whereas the current was dependent on Vgs minus Vt. It means the spacing between the curve is linearly dependent, not a quadratic dependent. And we have also discussed a strange result which says that when you incorporate the velocity saturation, then IDS is independent of channel length, independent of channel length. We have explained this phenomena in terms of transit time. We said that if you do have a MOSFET and the carrier will take some time to reach to drain moving from the source, that is what transit time. The transit time was directly proportional to L, and the total charge which is available in the channel is also proportional to L, and hence the current is independent of L. So it is not a function of L. So now let us see another short channel effect, which is historically the first short channel effect to be studied even before the modern scaling issues were identified. This is called CLM, a channel length modulation. This results a non-zero slope at the output characteristic. What we have discussed in our previous analysis, that when you plot the curve IDS versus VDS, or output characteristic of the MOSFET, then you will find that after a certain voltage, which we call it as VDS dash, the slope is 0, meaning this current graph is exactly parallel to the x axis. However, when you incorporate the CLM, meaning in the short channel devices, this shows a non-zero slope, which will give you a non-zero output resistance or non-zero output conductance when you incorporate these devices in analog circuits. So, the physical origin of this non-zero output resistance or conductance is defined in terms of CLM. To understand this, let us consider a MOS structure. Here this is source, this is drain. Let us consider we have applied the drain voltage in such a way the velocity saturation attained. It means the voltage between source and drain is what? VDS dash. So, throughout the channel the velocity saturation attained, carrier attained its maximum velocity Vd max. Now, as we know, the current is given by product of inversion charge into velocity saturation into W. So, if the carrier attained its maximum velocity, the inversion charge will go to its minimum possible value. Ideally, Qi should go to 0 and Vd should go to infinity to maintain a constant current. However, this is not physically possible, and hence what we have discussed in previous lecture, that Vd attain its maximum value. So, Qi will go to its minimal possible value. That is what we are observing here. But the question is, what will happen if you increase the VDS, the drain voltage, beyond this VDS value? So, if you see closely here, you are increasing the drain voltage beyond VDS dash point. So, here to support this product to be constant Qi dash and Vd, right, this region will get shifted to this side, and hence in this region ideally the inversion charge is very, very small, or you can mimic this region as a depletion region. And we know from our basic fundamental that delta square V divided by delta x square is equals to Q into Na divided by epsilon, a Poisson equation, which simply says V is nothing but Q into epsilon s divided by Q into Na divided by epsilon s into x square. It means in the depletion region, to support the voltage, the expansion of the depletion region is quadratic, and hence if you increase the VDS, ultimately you are increasing the reverse bias here beyond the saturation value, and to support this voltage, which is nothing but VDS minus VDS dash, the depletion region or the region is expanded in this direction. In this region, ultimately Qi attain its very minimal value and Vd is saturated, or Vd attain its Vd max value. So, the channel length, effective channel, so the effective channel length is now this much. Let us consider the length of this expansion is Lp. So, the effective channel length you left with L minus Lp, which means when you increase the voltage beyond the saturation point, the channel length is get modulated. That is what it's called channel length modulation. Channel length modulation. And if you see in the output characteristic also, we are talking about this voltage VDS dash. So, in the x axis you are sweeping the VDS, and the moment you go beyond VDS dash, there is a LP comes into picture, correct, and that is what the effective channel length is get modulated. This is the basics of channel length modulation. We can see how this channel length modulation affects your drain current equation. So, in general we can write the drain current equation as W divided by L into mu into COX dash VGS minus VT whole square in saturation. So, we can simply conclude that IDS is inversely proportional to channel length. Now, when you increase the channel length, when you increase the drain voltage, ultimately the channel length is no longer L, it becomes L minus LP. So, the new current including the channel length modulation effect is can be given as I ds dash divided by L minus LP. If you take LP, or if you take L out, you left with I ds divided by L into 1 minus LP by L. And you can rearrange this equation as I ds into 1 minus LP by L to the power minus 1. Again, considering this LP, expansion of the depletion region near the drain, is very much small as compared to L. So, you can simply rewrite this equation as I ds dash into 1 plus LP divided by L. Do not get confused here that this I ds does not comprise L here. I am just separating out, and I said that this is my I ds. Or you can, to get a better notation, you can rewrite as I double dash divided by L, and now when I incorporate or when I included the L, you can simply say I ds dash. So, ultimate the drain current equation can be written as I ds dash into 1 plus LP by L. You can simply relate this when the channel length is very much large, then the expansion of the LP compared to L is insignificant, and hence you can simply ignore this part. So, in the long channel length device, I ds is equals to I ds dash, whereas in short channel devices, I ds should have this LP term, I ds into 1 plus LP divided by L. Now, if we calculate LP, we can calculate what is the effect of CLM in our drain current equation. So, let us calculate the value of LP. So, I am redrawing the structure mentioning this point and this point. Let us consider, for a sake of simplicity, this point is 0 and this point is LP. Over this LP length, the voltage drop is VDS minus VDS dash. This is drain, this is source. We will start from basic one dimensional statistics, considering delta square psi divided by delta x square is equals to minus of rho x divided by epsilon s. Here rho is the total charge available in that region. As we have pointed out that in this region the inversion charge is negligible, Qi dash is negligible. So, the total charge is nothing but the substrate charge, or you can rewrite this equation as delta square divided by delta x square, or d square x divided by dx square is equals to minus of q into Na divided by epsilon s. This can be rewritten in terms of electric field as d of Ex is equals to q into Na divided by epsilon s. Now, let us consider some boundary condition. Exactly at this region where this LP starts, it means where this at x is equals to 0, this electric field is E1, and exactly at LP the electric field is defined as Em. So, we will use this equation to find out some boundary condition and closed form equation for LP. So, we can simply rewrite this equation as Ex is equals to q into Na divided by epsilon s into x plus C1. To find out this constant C1, I can put a boundary condition at x is equals to 0, E of 0 is nothing but E1. So, this will give me Ex is equals to q into Na into x divided by epsilon s plus E1, where E1 is the electric field exactly at this point, where we can consider that the carrier attain its velocity saturation. We can again replace this as d psi by dx or dV by dx and put a proper limit to find out the LP in relation with the voltage. So, I am solving this equation here, which will give me integration 0 to VDS minus VDS dash, because the voltage which is dropping across the LP length is nothing but VDS minus VDS dash into dV is equals to q into Na into x divided by epsilon s plus E1 into dx, and the limit of this dx is 0 to LP. So, this will give you a quadratic equation as left hand side will give you VDS minus VDS dash, right hand side will give you Q into NA divided by epsilon S into 2 into LP square plus E1 into LP. Correct? We can rewrite this equation as Q into NA divided by epsilon S into 2 LP square plus E1 into LP minus VDS minus VDS dash is equals to 0. Again we can solve this quadratic equation for LP as LP is equals to minus of E1 plus minus square root of E1 square plus VDS minus VDS dash into 4 into Q into NA divided by 2 into epsilon S divided by 2 into Q into NA divided by 2 into epsilon S. This 2 and 2 get cancelled, this 2 is cancelled with 4 and becomes 2. Now what will be the sign, whether it is plus or minus? It will be plus, because if I take negative, the length will be negative, which is not possible. So ultimately LP will be minus E1 plus square root of E1 square plus VDS minus VDS dash into 2QNA by epsilon S divided by Q into NA divided by epsilon S. So from this square root term, take this term out. You can rewrite as minus of E1 plus take this term out as 2 into Q into NA divided by epsilon S. So let me rewrite as the denominator will be Q into NA divided by epsilon S, right? Q into NA divided by epsilon S. Now here you will get square root of 1 plus VDS. So for sake of simplicity I am solving here. This will give you LP is equals to, take minus E1, now this is plus, take square root of 2 square root of Q into NA into 2 divided by epsilon out, you will left with E1 square into epsilon S divided by 2 times of Q into NA plus VDS minus VDS dash divided by Q into NA divided by epsilon S. So when you solve this equation, ultimately you will ended up with this. Considering phi d is another term which defines as epsilon S into E1 square divided by 2 into Q into NA. This is clearly observable that LP will start from 0. It means at VDS is equals to VDS dash, right, the LP will be 0. The moment you increase the drain voltage beyond this value, VDS dash value, the LP will start from 0 and ultimately it will expand like this in the source side to support this voltage drop of VDS minus VDS dash in that depletion region. So this is a simple 1D picture what we have derived for LP. We can put back into our equation and calculate the dependence of channel length modulation on the current, which is nothing but IDS dash into 1 plus LP divided by L. But strictly speaking, this is not a 1D analysis. We should go for 2D analysis, because in this region the voltage is from top as well as from side. So ultimately we need to solve a 2D Poisson equation. So and then we will come to these equations. Let us solve a 2D Poisson equation in some sense to calculate the LP. So I am writing a 2-dimensional Poisson equation, which is nothing but delta square psi, which is a function of x and y, divided by delta x square, plus delta square psi, which is a function of x and y, divided by delta y square, is equals to some charge, right. Here I am taking 0. For the simplicity, we are making the 2-dimensional Poisson equation to 2-dimensional Laplacian equation. considering that there is no immobile charge or there is no mobile charges are available in this region, and hence we can simply solve this equation for simplicity. So this equation can be rewritten as, by considering psi xy as two separate functions, one is a function of x and one is a function of y. So we can rewrite as capital X and capital Y, where capital X is a function of x only and capital Y is a function of y only. So this can be written as 2 in d square by dx, d square x by dx square into y plus x into d square y divided by dx square is equals to 0. Or you can simply rewrite as 1 over x d square x divided by dx square plus 1 over y d square y divided by dy square is equals to 0. This equation can be solved only if these two factors will be equal to a constant. It means 1 over x d square x divided by dx square is equals to k square and 1 over y d square y divided by dy square is equals to minus of k square. When you solve this equation, ultimately we will get x is equals to some constant e to the power of kx plus b into e to the power of minus kx, one solution, and one is y is equals to c into cos of ky plus d into sine of ky. Now we need to use some boundary condition to find out these constants. Let us see what are the boundary conditions. In y direction, if you see at y is equals to dj, where dj is this depth, it is called junction depth. At y equals to dj, if you see, right, then the potential is considered to be 0. So psi y is considered to be 0, because in surface potential condition also we said that we are considering some point in the body with which we measure the surface potential. So at y is equals to dj, we can say psi equals to 0. So we can use this equation to put psi y, meaning the capital Y. So it is equals to 0 is equals to c cos 0 is c plus, so c is equals to, so we need to have some boundary condition. We said that at y equals to dj, psi y is equals to 0. So we can use this equation where capital Y is nothing but psi y, which will give you what? 0 is equals to c cos of k into dj plus d sine of k into dj. You can simply rewrite as tan of k dj is equals to minus c by d. To solve for a first eigenvector or first eigenvalue, we can simply say k times of dj is approximately equals to pi by 2, or we can rewrite as k is equals to 1 over dj, where dj is junction depth. Similarly, we can use another boundary condition for y is at this junction the electric displacement should be continuous, and hence we can rewrite as epsilon s dy d psi y divided by dy at y equals to 0 plus, it means exactly at this point, should be equals to epsilon ox psi divided by t ox at y equals to 0 minus, right, exactly at this point. So at that point the electric displacement should be continuous. So what we will do, epsilon s into, you differentiate this function, you will get minus c sine of ky into k plus d k cos of ky and put y equals to 0 should be equal to epsilon ox. Now put y equals to 0 in psi y, you will get what? C divided by TOX. From here you will get epsilon s into, if you put y equals to 0, this function will be 0, you will left with d into k is equals to epsilon ox into c divided by TOX. Now if you put the value of c by d, which is nothing but k into dj, then k will get cancelled from both sides and ultimately you will lose the eigen factor. So, to incorporate the eigenfactor, you can use 10x is equals to x plus x to the power 3 by 3 plus higher order terms. So, instead of using k dj, you can use k to the power 3 dj to the power 3 by 3. If you solve like this, you will ultimately get k is nothing but square root of epsilon aux divided by epsilon s into T aux into dj. This is the value of k you will get. Now, we can define a characteristic length which is nothing but L A is equals to 1 over k, which is nothing but what? Square root of epsilon s by epsilon aux into T aux into dj, which is given here. Why this 3 factor is coming up? We have already discussed in a very in our previous lectures that the permittivity of semiconductor or silicon is 11.7, you can consider it as 12. Similarly, the permittivity of oxide is 3.9, you can consider it as 4. So, ultimately you will get a factor of 3. So, the characteristic length La can be given by square root of 3 times of Tox and dj. This will give you an intuition whether my CLM is more or less. For example, if Tox is more, meaning the oxide thickness is more, the gate control will be weaker, and hence what will happen? The CLM will be more. Similarly, if the junction depth will be more, the CLM will be more. Now, to move further, we need to solve some boundary condition in x direction, because we have some factor of x also. So, this x is nothing but psi of x, which is given as a e to the power of kx plus b e to the power of minus kx. We can simply find out the electric field as d psi by dx, which is nothing but a into k e to the power of kx minus b into e to the power of minus kx into k. Now, at x is equals to 0, the electric field was E1, and at x is equals to Lp, the electric field was, or electric field is defined as maximum. You can see here we have defined a critical field EC, which says that at this point the carrier attained its maximum velocity. After this, the electric field increases in this region, right, because the voltage here is increases, which is nothing but VDS minus VDS dash, and here it attained its maximum electric field, which is defined as EM, where we can relate this equation as EM square minus E1 square is equals to VDS minus VDS dash divided by LP whole square. So, this electric field, which is a 2-dimensional electric field here, can be related like this, and by using these boundary condition, ultimately you will ended up LP is equals to LA into log of VDS minus VDS dash divided by L A plus EM divided by E1. So, this is the equation which we can obtain from our 2-dimensional analysis, like we can show it here. So, this will be the final outcome of 2-dimensional analysis, which shows that my length LP is related with these many parameters. Now, from here if you take EM out, ultimately what you will get, LP is equals to LA log of VDS minus VDS dash divided by EM into LA plus 1 divided by E1, correct. This will be inside the log. Now, this is defined as VE. VE is the electrostatic fitting parameter, which we are representing in terms of voltage, because this is also in voltage. So, these all analysis will give you the final result of LP as this. Now, we can simply say that log of 1 plus epsilon is approximately equal to epsilon if epsilon is small. So, we can replace this LP as LA into VDS minus VDS divided by VE, where I said that VE is nothing but EM into LA, correct, which is nothing but a electrostatic fitting parameter we need to include to capture the CLM effect in our model. this equation can be rewrite as IDS is equals to IDS dash into 1 plus LP divided by L. That is what we have derived. So, if you put the value of LP, which is nothing but this, you will get IDS is equals to IDS dash into 1 plus LA by L into VDS minus VDS dash divided by VE. Here we are defining another term which is VA. VA is nothing but VE into L divided by LA, where VE is the electrostatic fitting parameter, L is the channel length, LA is the characteristic length, which is 1 over K we have just defined, right. So, ultimately the current equation can be given as IDS is equals to IDS dash into 1 plus VDS minus VDS dash divided by VA. Here VA is in loosely word, here VA is called as early voltage. In hand calculation can be represented as VDS into 1 plus lambda into VDS, where lambda is nothing but 1 over VA. So, to incorporate the channel length modulation, the complete current equation in the saturation is can be given as W divided by L mu into COX dash into VGS minus VT whole square divided by 2 into alpha into 1 plus lambda into VDS, where lambda is channel length modulation parameter, right, which is nothing but 1 over VA. So, in general circuit theory or hand calculations, we use this equation which says that we are incorporating the channel length modulation effect in our drain current equation. Now, what will happen when you go from non-saturation to saturation, incorporating the channel length? As we have already discussed when we were discussing about velocity saturation, that the saturation, that the transition from non-saturation to saturation is very smooth. If you incorporate the CLM parameter in your model, then CLM gives a non-zero slope, meaning this green line is a CLM line, right, and this red line is the line which is you are obtaining from our model. It means at the transition there will be a discontinuity. Thus, a proper attention should be given while modeling the CLM and incorporating in our basic model. That is what we have said, that it is very important that how much we can save with a minimal modification. Thus, an accurate MOSFET modeling requires proper attention to include this kind of effects to ensure physical stability of the model. Let me summarize that in this lecture we have discussed about channel length modulation, which will give you a non-zero slope in the output characteristic, and in a hand calculation we can simply rewrite this equation as IDS dash into 1 plus lambda into VDS. Strictly speaking, to incorporate the CLM effect, you need to solve a two-dimensional Poisson equation in that region, where the channel is modulated by length LP. So, that is what we have seen, that overall current is modulated because of the channel length modulation as IDS dash into 1 plus LP divided by L. So, we will stop here for today. Until then, take care.